For this apprenticeship exercise, we are going to reinvent our own version of some of the string library, standard library manipulation functions. So the idea here is that, yes, those functions have already been implemented well, better than we are going to do in this exercise, okay? But re-implementing them is kind of one of the best exercises to make sure that you understand how those functions operate, but also that you understand all the principle on manipulating strings in the C programming language, right? So let's jump into the code. I already prepared a little bit the code here so that we don't start completely from scratch, just to save us a little bit of time on the video, removing the stuff that's not super interesting. So I have a test.c that is actually including hsl.h. So our little exercise is going to be called the handy string library, so hsl. We include hsl.h, so the header file for that library. We have a main that does, for now, nothing, but we're going to write some form of testing there, tinkering with the function that we write. Then we have hsl.h that I just mentioned. So this one contains the headers, the prototype, for all of the functions that we have to actually write, okay? And then we have hsl.c, which is going to contain the implementation of all of those functions, as usual, okay? So I follow the traditional separation of code, you know, into tools.h, tools.c, and main.c, for example, test.c. So I just applied it here to the library. We have, what do we have here? We have, for now, dummy implementations of all of those functions. So any function that was supposed to return an int is going to return 0. Any function that was supposed to return a pointer is going to return null for now. So if we were trying to use that, of course, it would not work that well. But at the very least, what we can do is we can say, I want to compile test.c and hsl.c, make sure that it's syntactically correct. And then, of course, if I run it, I get like a return exit success, which is not really doing much. But we are going to fix that. All right, so now we can jump into actually implementing the functions that are required of us to implement. The first one is Hsl Length, so handy string library length function that measures actually the length of a string that you pass, a well-formed string that you pass as parameter. So the instruction specifies that if the pointer s here is null, then the length of a null string is going to be 0. And if I have like, if I have n characters in my string, then I want to return here I want to return the size of the specified string, not including the \0 at the end. So not including the n+1 character. All right. I hope this makes sense because this was kind of a little of a fumble here. So it's going to make more sense when we implement it anyway. Let the code speak. So let's go here and let's start by saying if s equal null, return 0. Okay, we get that out of the way. And we're going to do the same for every function we implement in this exercise. We're going to always try to get rid of the validation test, you know, the make sure that the parameters are okay up front in the function code. And then as soon as we have an opportunity to return a value, then we do it. We get rid of the easy case, pretty much. So if s equal null, return 0, you know that null is defined actually as the value 0, or the conversion of the value 0 into a void pointer in stdlib. So that means that it's false. So if I say if s, and with a not in front of it, if not s, okay, if not s, that means if the negation of the pointer s, if it's null, is going to be false, interpreted as false. Negation of false is going to be true. That's going to trigger that if statement. So I'm returning 0 here if s is null. This is just another way to write it. But if you are more comfortable writing, you know, if s equal null, by all means, use that. Okay, this is not a problem at all. I just want to point out the alternative notation that are commonly used in the C programming language. So we got rid of that first part, okay? That was the easy part. And now what we want to do, we want to count how many characters are in the string S and return that number, not counting the \0. So we behave the same way than strlen. Okay. All right, so how are we going to do that? Well, let's start by saying that we need a counter, count equal 0. Okay, and I'm going to have a while loop that's going to start with S, and is going to actually keep iterating while S index count is different than \0. And then inside, I'm going to increment my counter. And then at the end, I want to obviously return the counter. Well, let's see if that compiles first, and then we're going to add some code to our main to test it. So it compiles, so syntactically this is correct. Let's go in the main, and let's say that we have a first string. We're going to use string literals here because we don't care if the strings are immutable. Char star S1 equal hello there. And then I'm going to do a printf string %s is %d characters long. And we're going to see what this tells us. Okay, so string S1, and then I'm going to call Hsl, what do you call, length, and S1 as parameter. Okay, so I just want to visually inspect that, the string that is given here, and I'm going to put like square brackets around here so that I know exactly if there is a space heading, an extra space at the beginning or not, or an extra space at the end or not. I want to visually inspect that this string is indeed n character long as reported per Hsl length. So in our case here, what do we expect? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we expect 11 character long. That function, once again, is not expected to count the \0 at the end. So let's compile again. Let's run it. String hello there is 11 character long. So I would do more testing in practice in a real world scenario. So I would say, for example, let's call it S0 because it's going to be our empty string. So char star S0 equals, actually, you know what? S0 is going to be the null string, and char star S1 is going to be the empty string. And yes, an empty string is not the same thing as a null string. Okay, a null string, that just means a pointer that's supposed to tell you where the string is, contains the address null. So there's no string whatsoever to talk about. Okay, an empty string like this one, double quote, nothing, double quote, is a string that exists in memory, but it has an address. So there is an address in the pointer S1. However, at that address, what you find is only one character, the special character \0 that marks the end of the string. So this is a string that is technically in memory one character long, just the marker of end of string. And then we're going to keep S2 here as being our original string. And what I want to do now is I want to do a few printf here. I'm going to be lazy and cut and paste the stuff. There we are. And we're going to do S1, S0, S1, S2. So let's start with S0, S1, S2, and again, S2, S1, S0. All right. Let's compile this and run it again. Okay, so the string null, printf is nice enough to display like this, when we pass a pointer to a string that is null and try to display it as a string, it's nice enough to indicate to us that this was a null value here that was passed. Is 0 character long, string empty string is 0 character long, string hello there is 11 character long. Okay, I think we are done with this first function. Okay, so easy function, not much code to it. Now what I'm going to do is I'm going to refactor it a little bit. Okay, just so that you are exposed to common ways, alternative way to write stuff. Okay, what I have here is s of count different than \0. So here's the interesting thing about the character \0. The character \0 has as an index in the ASCII table the index 0. So what I'm really doing here is I'm trying to check if this is 0. And you'll see some programmer also compare this to the character, compare the end of string marker to the value null. Okay, value null, value 0 depend on the convention in your team, I guess. So I could write something like that, okay? But we know also that something that is different than null is true. Something that is equal to null is false. So I could get rid completely of all of that stuff and just say while s count plus plus. Okay? If I do this, let's go, compile again, run again, still working, no problem. Okay? Now you might be tempted to say, well, first, those curly braces are useless because I have only one statement. That's a given. Okay, no problem, no argument there. But you might be tempted to say, I want to do the plus plus here. So let's do this. And we have a loop that has an empty body. We're going to put a semicolon here. And we remove that count plus plus. So this is like just compact, okay, maybe too compact, I don't know, depending on your test, but taste, sorry, not test. But it, it's supposed to do the same thing, except that here it's off by one. It's off by one because what's happening? So pause the video, try to figure out, then unpause, and I'll give you an explanation. What's happening here is I do the plus plus here, regardless of whether this is true or false. So that means that when I reach finally the end of string marker, I realize that I reach the end of string marker because s index count is the end of string marker. However, regardless, I increment the pointer s. What I was doing before is if I did discover that I was at the end of string marker, then only if I was not at the end of string marker, I would increment count, which was actually the desired behavior. So it's up to you. You can either write it like this, which maybe is cleaner, I don't know, easier to grasp, understand, or you can write the shorthand version, like this, everything on the same line, but then you'd have to do count minus 1. Okay, so it's completely up to you which one you prefer. I'm just giving you options here pretty much. Okay, so compile, run. This is working as it used to work before. What else can we refactor here? Well, instead of using the square bracket notation, the array indexing notation syntax, I could use actually the pointer syntax, right? The pointer arithmetic syntax. So the first thing I could do is straight translation of this. There we go. S plus count plus plus. Okay. Again, it's a matter of preference, I guess. Okay. I think this is maybe a little overcomplicated. It doesn't look as clean to me as the array notation in this example. But if you want absolutely to use the array pointer arithmetic notation, then what I would encourage you to do is something like this: star s plus plus. So use incrementation of pointers. Okay, increment by the next offset to skip over the next character. If we do that, let me see if I need to modify something else. We could get rid of, well, if we still have count, we need to increment count at some point. So I would still have to do something like go count plus plus. So we're going to make it shorter, don't worry. We're going to explore every possibility that I can think of on how to write this. So here's a way to write this, okay? I iterate for my string. I start with the pointer s as the first character of the string. Then I check if star s is actually true. Star s being true means it's not the end of string marker. Regardless of whether it's true or not, I increment s. And then if it was true, then I keep looping again. I keep incrementing s, and every time I increment my counter, and at the end, I return the counter. So if I'm not off by 1 here, we should have the same result. Yeah, okay, we have the same result. And this is bothering me a little bit because I increment s and then I increment a counter. Can't I do something a little different here maybe? Yes, I can. Let's try to get rid of this counter altogether. Okay, so I want to get rid of the counter. I want to only iterate through my string and increment s every time. And then at the end, what should I do to try to measure the length? Well, I have s that points, to the end of my string now, to the end of string marker, pretty much, and I have the original s that was the beginning of the string. So I want to measure the difference between the original start of the string, and the current position of the pointer. To do that, I just need to save in a variable, let's call it start, the original value of s. Then I increment s. I go up to the end of the string, to the end of string marker, and then I compute the difference here. And let's take a look at how this works. There we go. And it's off by 1, so we're going to correct that here. It's the same problem than before. Okay, I increment s even though I reach the end. So if I do s minus start minus 1 here, this is going to probably fix the problem. It did. So there we go. We went through how many? Four maybe? 4 different ways of writing this very simple function. As long as you provide code that works, I'm happy during an exam, okay? So you can opt for the version that you prefer, that is the most natural to you. However, you should be able to understand each of those versions, because they are proper C language version of the exercise solution. So you need to be able to read different type of code than the code that you personally prefer, okay? And this is a good review also on pointer arithmetic and stuff like that. So it's all good. All right, so we are done with str length. What do we have next on the menu? We have str compare. All right, so str compare is going to, as the name implies, Hsl compare is going to compare two strings, s1 and s2, and tell us whether they are the same or not. And the convention is return 0 if return 1, if the strings are identical, return 0 if they are different. So this is the opposite actually of what strcomp does. strcmp is a standard C library way of comparing strings. We have a different implementation here. The meaning of 0 and positive number, negative number, totally different. So watch out for that, okay? Just in case you are using strcomp in your test to compare, how your implementation is faring. We're going to do our own test here based on the requirement that we received. So Hsl compare, let's see what we can do here. So we are going to start again trying to get rid of the basic situation that are easy to resolve, okay? What is easy to resolve here? Well, if the two strings don't have the same length, then they are definitely different. So I could say int size 1, size 2, actually, you know what, int size 1 equal, and I have something to measure the length, right? Awesome. Hsl length s1, okay? And then I'm going to do the same for s2. Here we are. I'm going to measure the length of h2, store that in a variable int size 2. Okay. And then once I have this, I can immediately get rid of the easiest scenario. The easiest scenario is if size 1 is different than size 2, then forget it. Oops, and forget it means return 0. Okay. And actually, you know what? We are going to change this a little bit. We're going to change this a little bit. Let's use bool. We are going to use a Boolean data type, and I'm going to do true false. So I'm making a little change here in the instruction. I might update the instruction afterward, okay? But the idea is that this is business of 0 and 1. Since we detect only if they are or they are not the same, then let's go back and check with a Boolean. So I do have an include of std bool.h here to make sure that I can use the Boolean data type. Okay, except that I spelled it wrong here. So there we go. We're going to fix that. So I want to use the Boolean data type, and I want to update here as well my prototype for the function, so that it says that we return a Boolean value instead. And I'm going to use the constants, true and false, just to make the code a little bit, I guess, a little bit cleaner, right? Makes more sense to me. So if the size are different, return false. For now, and otherwise we return true. Okay. And then in between here and the return true, we are going to check what's going on character per character. So we want to iterate over the two strings, but we know they have the same size now. So we want to iterate character by character over the two string, compare each character to the character that occupies the same position in the other string. And if we find out that there is even one difference, just one difference, then that's enough for us to say that the strings are different from one another. So we're going to return false. So let's implement this. We're going to use a for loop for int I equals 0, I lesser than, and I could use size 1 or size 2 here, it doesn't matter. Okay, I plus plus. And then I don't need curly brace because I'm going to have only one statement inside my loop. The statement is going to be if, and so I'm going to look into S1 at index I. So I'm using the array index notation here because that's the most convenient for what I'm doing, okay? And I'm going to say that if this character is different from its counterpart in S2, then I want to return false, okay? Let's save this. Let's get rid of any typo that I may have left behind. If we run it, it's not going to do much more right now, but I'm going to go in the main, and I'm going to add some more tests here after our first test. So here's the first block of test. Okay, and I need another string, char s3 equals, and I'm going to say hello there as well. Okay, and now what I'm going to say printf string and person s r. And now what I want to display here is a string s1, string s, let's start with s2 and s3, and then I'm going to call Hsl Compare. There we go, s2, s3, and I'm going to use a ternary conditional operator, just good practice, okay, don't forget about those. So question mark, if it returns true, then I'm going to say the strings are identical. If it returns false, I'm going to say the strings are different. Alright, and close this parenthesis here, and we are done. So I'm going to put that on the next line so that it fits nicely. Let's test this. So save the file. Wanting too many arguments for format printf. What did I do? Oh, yes, I forgot to include this last string here. There we go. Get it out. So these three first line, I'm going to comment them out. We don't need them, but string hello there and hello there are identical. Okay, this is nice. This is what I expected. Just for the sake of testing a little bit more thoroughly, maybe I should cut and paste this and then compare. Maybe what do we have that's interesting? Well, what if I compare S0 to itself? Okay, so two null strings. Or then I compare S0. I need to modify this here as well. And then I can compare S1 to S1. There we go. And then I'm going to add one more. I'm going to compare, so let's see what we have, S2 to S4. And I'm going to create S4 in a second, okay? And S4 is going to be the following: char star S4 equals hello there. And what I did is I changed the lowercase L into uppercase. That's it. But that's enough for the string to be different, right? So here we are. So let's keep those on the screen. And hopefully S0, 0, S1, S1, S2, S4. Yeah, hopefully they're correct. And we are going to compile this, and we are going to run this. So what do we obtain? String hello there and hello there are identical. Awesome. Happy to learn that. However, I just realized that I'm lacking a backslash n here to make things more readable on the screen. So I'm going to fix that first. And then we're going to rerun, and we'll have somewhat of a better time reading the output than right now. All right, run it again. There we go. So hello there and hello there are identical. I think we can agree on that. String null and null are identical. Well, technically true. Empty string and empty string are identical again. Perfect. That makes sense. String hello there and hello there are different. Yes, they have the different spelling here. So what else could we possibly test here? We could test two strings of different size, and I think with that we would have covered pretty much every possible test that I can think of. Okay, so I'm going to add one more here, and I'm going to say char star s5 equal hello. Did I have uppercase H? No. All right. So I'm looking at S2. I want to spell it exactly the same way that I spelled it in S2. And I want to compare S2 to S5, but of course, this is just the beginning of the string, okay? So it should tell us that the strings are different. So let's save. Compile, run, and it tells me indeed that hello there and hello are different. So I think we covered pretty much like the main scenario here that could be relevant. I'm going to start commenting things a little bit, like for example the output that was testing, Hsl length. We don't need that to be displayed every single time. And then I'm going to comment also the output that we just implemented here to test that other function. I'm going to keep the definition of char, S3, S4, S5, etc. All of those strings that I define, I'm going to keep them because I'm going to reuse them in my future test. Okay, so might as well not have to redeclare all the time new strings like this. So there we go. Now it should not display anything anymore, but we are going to be ready to test the next function that we have to write. So Hsl length is done, Hsl compare, Hsl allocate. So this one is going to be super easy. So the idea here is we want somebody to tell us, I want a string of 5 characters, not counting the end of string marker, okay? And what we are going to do is we are going to allocate for them a string, and we are going to return the address where that string starts, but we are going to take into consideration the fact that we need one more character for actually the end of string marker. Okay, so this is going to be literally a one-line function here, and I'm going to go ahead and put that here. There we go. So the return here is going to be the malloc that we do normally by hand. Okay, so return char star malloc size of one character times the size that was requested as argument plus 1. And if I match and balance my my parentheses, then this is all we should have to worry about. Okay. So testing this is a little bit more difficult. Okay, because I can allocate memory. Sure, I can make sure it doesn't crash. That would be already a plus, I guess, right? So hold on, let me go here and say char star S6, it's not going to crash, but just to be for char star S6 equals Hsl allocate, and well, I'm going to prepare myself to make a copy of the string S5, right? So I'm going to call Hsl length of S5. So Hsl length of S5 tells me how many characters, not including the backslash 0. So it's going to be 1, 2, 3, 4, 5 in this case, hello, okay? And then I pass that value to Hsl allocate that says, oh, you want to do us a string with 5 characters, so you're going to need 6 characters in memory. So I add a +1 to that, and now S6 points to an area of memory that has been properly allocated and that is able to contain 5 characters plus an end of string marker. So later on, if and when I want to make a copy of hello into a new string, for example, I could make a copy right there. So I'm calling the allocation, but I mean, besides the fact that it doesn't crash, it's not going to give me much more information, okay? So compile, run it, yeah, it's still running. I commented out all the other printf, so we're good. What else? I think that's pretty much it for this one. This is really a one-liner. But the next one, deallocate, there are 2 versions that are asked of you in actually the instruction. And I have only one version here right now in my file. So I'm going to fix that, deallocate. And the idea is that one is going to be called deallocate. The other is going to be called deallocate cleanly. Deallocate is going to take a char star p as parameter. Deallocate cleanly, for a reason I'm going to explain to you, is going to take a char star star p as parameter. Okay, so we have those. I can go back to hsl.c and allocate is done. So here is deallocate. And I'm going to make a copy of this code here, and I'm going to call it deallocate cleanly. And I'm going to explain what I mean exactly by cleanly, but it's explained in the instruction as well. Let me just compile real quick to make sure that the prototype match the function signatures in the C5. So let's start by the easy one, deallocate. So deallocate, it's going to be another one of those one-liner. You allocated previously, potentially with HSL allocate, a string of whatever size, and now you want to deallocate it. You give me the pointer to that string. I free that pointer. Okay, and that's all there is to it. Now, to be safe, what I could say is if P, then free P. Because if P allows me to detect, to make sure that P is not null, okay? If P was null, I don't want to free a pointer that is set to null. This is going to cause my program to crash, actually, right? So instead, what I'm saying is that if P is not null, then actually free it. Otherwise, do nothing, okay? It's a void function, doesn't return anything, so do nothing. The instruction were more specific than that. I'm taking a look right now, and they say, by the way, I want you to return some value, depending on whether the allocation went fine or not. So we are going to use, and I'll update the instruction accordingly. We're going to use Boolean here too, and I'm going to say, so if not P, return false but do nothing, else freeze the pointer and return true. So it's just a way to say, did the deallocation go okay or not? All right, okay, we can deal with that. What about deallocate cleanly? So what is the difference? So let's start by doing a cut and paste. I want to start with the same base, okay? So if not P, but this time I'm not given the pointer directly. I'm not given the address at which the string that I want to deallocate is located in memory. What I'm given is the address of the pointer variable that contains the address where the string has been allocated. So there is one more level of indirection here, right? So that means that when I reuse this code that I wrote there, I'm going to have to take into consideration that level of indirection. So here, I'm going to have to say if not star p, which I could write as if star p equal null, okay? Pick your preference here. If you think that this is clearer, less prone to error, then go for it by all means. If star p equal null, then forget it. The pointer contains null. I don't want to free a pointer that is null. Return false. When I go and proceed to free, I'm freeing star p, okay? Remember, p is the address of a pointer variable, so I dereference this address, I find the pointer variable, and then I look at what's in the pointer variable. That's the address of the string. That's what I want to pass to the free function to deallocate that string. And why do we call it HSL deallocate cleanly? Because we are going to then set that pointer to null. And this is the whole reason for which I needed this double indirection. I needed a pointer on a pointer. If you just give me, if you pass as an argument, the pointer that you have on your string, I can deallocate the string because you gave me its address. But I cannot change anything inside that pointer that you are using, for example, in the main or in whatever function called Hsl deallocate. If you give me the address of your pointer variable, then I can do something more for you. I can make sure that after I deallocated, I set it to null, which is going to spare you a whole category of bug whereby you deallocate a pointer, but you forget to set that pointer to null, and then later on you try to use it, and so on and so forth, blah, blah, blah. So we are going to change the return value here as well. We're going to make this a Boolean, and we have our return true, return false. Let's go back here to the signatures, the prototype, and make sure that we also have Boolean as a return data type. Let's save all this. Let's compile. Compiles right. If I run it, I'm not really testing anything here, so it's still working. But what I can do here, I can attempt to deallocate. So printf deallocating, and I'm just going to write the name of the pointer S6, and I'm going to here display whether it's a success or not. Okay. So I'm going to put that like this, and I'm going to call str deallocate S6. Okay. And I'm going to use a ternary conditional operator. I'm going to say success or issue. Oops. All right, awesome. So I allocate S6, then I try to deallocate it. It's going to tell me if it's successful or not. Let's try just that for now. Compile. Oops, what did I forget? Implicit declaration of function str deallocate. Yes, because it's not called str deallocate. It's called Hsl deallocate. There we are. All right, let's try again. Compile. Run. Deallocating S6 success. Okay, so now if I do again, I'm going to reallocate another time using the same pointer H6, and then I'm going to try to deallocate. Well, actually, if I just reallocate it like this is stupid. So hold on, let me try to do something a little bit smarter here. Instead of reallocating, because I already checked that this works, what if S6 is null? Okay, that's pretty much the over case that we want to detect. So deallocating null pointer, and we are going to see that it tells us success or issue. I should have used success or failure, but anyway. And there is an issue, yes. So it detects appropriately that the pointer is null. So we tested deallocate. What about deallocate cleanly? Well, we're going to do exactly the same test. Here we are. And this time we reallocate some memory for S6. And I'm going to say deallocating cleanly S6. There we go. Hsl deallocate cleanly. And then I want to, in addition to that, I want to display the value of the pointer. So I'm going to display not only this, but I'm going to also display the value of S6 after I am done deallocating it. Okay, and I will do the same thing here. And I have to change how I call things. So here, when I call deallocate cleanly, I want to give the address of S6. And there we go. That should be perfect like that. So I'm going to test the case of null afterward, but first I want to make sure this one is correct. No. So I can deallocate cleanly S6 is a success, and then it gives me, of course, the address of the pointer. So it was not set to null. Well, kind of was. Hold on, let me show you exactly what I mean. Let's take this. Okay, we are going to stop this here, put the semicolon, and then I'm going to use another printf. I'm going to explain why, okay? It's actually an interesting source of misconception and bugs. So I display first deallocating cleanly S6, okay? I call the Hsl deallocate cleanly as address of S6 function. I use it in a ternary conditional operator, blah, blah, blah. And then when I'm done, I want to display the value currently held inside of S6. There we go. And it looks like I'm doing exactly the same thing, right? Well, now it tells me the pointer is nil, which means null, okay? So why wasn't it working before? It looked like I was doing exactly the same thing. Well, in the C programming language, the C standard doesn't guarantee the order in which your arguments are evaluated. We know that when you call a function, all your arguments are going to be evaluated one after the other, okay? And then it's the result of those evaluations that is passed as the argument, passed by value, to the function and assigned to the parameters. However, do I go left to right or right to left? Well, it matters here because when I had a printf here that called Hsl deallocate cleanly and then used it in an expression, and then the second argument was S6 itself, if you evaluate S6 first, then you are going to get the value of the pointer, and then you evaluate this argument, you call Hsl deallocate cleanly, it's going to change S6, but too late, you already used the value of the pointer, so you are going to display the value of your pointer. So by doing it in two steps here with two separate printf, I first make sure that I call Hsl deallocate cleanly on S6, I get the result that I wanted, and then I do another separate printf, so I'm sure that this S6 here is going to be evaluated after the call to that function, and it shows that it's actually set to null by the call to that function. So the order of evaluation of the argument is not specified in the standard, which means that different compiler implementer can go and adopt different strategies. They can go left to right, right to left, or they can go even in random order, or even go in whatever order they think is the best to optimize the performance of the program. So there's absolutely no guarantee. So in those cases, it's better to separate like that in multiple statements. And then, just to be thorough, we are going to do the same thing with null, but since we use pretty much the same code, we should expect that it's not going to be an issue. Okay, deallocating cleanly null pointer. It should tell me there's an issue, right? And then the pointer should be null at the end as well. So let's try that. Let's make sure. Was there an issue? Deallocating cleanly null pointer issue, yes. And then the pointer was null, but it was already null anyway, so I didn't do anything actually in the function here, in the function that I wrote, Hsl deallocate cleanly. All right, what else? We have clone. So the clone function, here we are. The clone function, its role is to actually take a string and deliver to me a copy of that string. So we are going to allocate enough room to store the new string. Okay, we are going to copy all the character in the newly allocated space in memory, and we are going to return that. So that one should be relatively straightforward, and we are going to try to use the other functions that we already implemented. So first I'm going to try to measure the length of S. So I'm going to use Hsl length. There we go. Hsl length of S is going to tell me the size. Then I want another, I'm going to call it TMP, another pointer on string, and I want to allocate a new string of size, well, S plus 1. Well, I have a neat little function that does that. I just pass the size of the string, and it's going to make sure to allocate enough memory for this many character plus 1. And then I want to iterate over every character in my string S and make a copy of that character into the string TMP. All right. So please note that here I'm allocating something, and inside this function, I'm not going to deallocate it. Why? Because I want to return it. I don't want to create a new string, then destroy it and return null, to whoever called me. That would be terribly useless, okay? So instead, I'm going to allocate that string, return the memory, and as far as this function is concerned, we are done. However, any programmer that is calling Hsl clone should know that he or she is now responsible for deallocating whatever pointer they received as a result of calling Hsl clone. Okay? So it's important that you understand that it's not always as simple as allocate and free immediately, allocate and free immediately. Sometimes you allocate in some part of the code you never free, and people will call that part of the code as the one that are going to be responsible for doing the deallocation. So in this case here, we're going to iterate with a loop, okay? And I'm going to use the same trick that I used before. So I'm going to say while star s. And while star s, I'm going to do my work, okay? And I'm going to save first the address where the string that was given to me as argument starts, okay? So that I can then increment my pointer star s. And I can say while star s, well, I want to copy inside TMP. So star TMP equals star s, TMP plus plus, s plus plus, or if you prefer, put all of that in one line. And we are going to say while star s, then star TMP plus plus, star s plus plus. Okay, post incrementation. And that should work for every regular character. And then at the end, star s is going to point to the end of string marker. So star TMP equals star s is going to allow me to copy that end of string marker. Or I could insert it myself by hand by saying, star TMP equal single quote backslash 0 single quote. Okay, I write down the end of string marker myself. And then what do I want to return? I don't want to return null anymore. I want to return start. Okay, I want to return I want to return I want to return TMP. I want to return what I just allocated right here. Okay, so this is a copy of my string. Well, let's get rid of syntax errors. And we do have at least one. Okay, so str allocate, I keep calling those things str underscore allocate and stuff like that because I'm thinking about like the standard string library. So Hsl allocate, Hsl length, Hsl allocate. Okay, let's go. Let's see if that makes the compiler happier. Yes, it makes the compiler happier. And now we need to, there's no point in running it right now because we have no test, right? But we are going to test it right now. So before we do that, I'm creating memory leaks here, I'm pretty sure. I called Hsl allocate, deallocate, allocate, deallocate. No, actually, no, I deallocated everything I allocated. Awesome. So now what I'm going to do is I'm going to take the string, let's take, for example, S5, hello. And I'm going to say I want, so this is S7 that we are at, Hsl clone S5. And then printf clone of, need to display my string, is my new string. And this is going to be S5 and S7. So I'm just cloning a short string here, but that should work. That should be enough for us to make sure that this is working, since the video is getting a little long already. So I don't see the clone of anything. It's because I didn't save my file. Here we are. Compile again, run it again. The clone of hello is an empty string. Well, that's not exactly what I wanted, right? Char star S7 equal Hsl clone S5. Let's go back to the code, see what we did wrong. Hsl clone, so I first measure the length of the string. I'm okay with that. Then I call Hsl allocate with that length. So Hsl allocate should be doing its work. Let's double check real quick. Yeah, it's a malloc size +1. So that's okay. Char star start equal S. Technically, I don't even need to store that. I don't know why I'm saving this. So while star s star tmp plus plus equals star s plus plus. That sounds good to me. And then here I'm going to make sure that I have star tmp. It has been incremented, so I'm going to put the end of string marker by hand. If I return tmp, of course, that's why I needed that start. If I return tmp, I'm at the end of the string that I created. So here what I need is char star start equal tmp. There we go. This is the one I want to save. Okay, and then return start. All right. Let's see if that works a little better. It should. All right, clone of hello is hello. So yeah, that works a little better, a lot better actually. Okay, so that's pretty much all there is for the cloning, except I could try to speed up things a little bit by saying if s equal null, so if not s, okay, whatever notation you prefer, if not s, return null. You give me a null pointer, I'm not going to make a copy of it. There's no string. I'm just going to return null, and therefore I'm going to keep measuring the length and getting a 0, then allocating something of size 0. All of this is not really appropriate, right? So I just shortcut everything. If you give me a null pointer, that's it, we're done. Here's your copy of a null string. It's a null string. Surprise. If you give me an empty string, well, yes, I'm going to copy an empty string. An empty string is a string with one character, just the end of string marker. So let's add those tests real quick here. So I'm going to use the empty string that we have. So hold on, I need to copy all of this actually. So H7 has been cloned. Before I do more tests, let's make sure that this one is clean. There's a little bit of a memory leak here because S7 has been made as a clone of S5. So I allocated some memory. So Hsl deallocate cleanly address of S7. Now my test is better. Okay, I allocated memory, I deallocated it, we are clean. Now what I want to do is I want to keep going like this, and I want to test two more cases. The first case I want to test is what happens if I try to clone a null string. Okay, so I'm going to call this S8, try to call the null string, and try to deallocate it afterward. And this is going to be interesting because Hsl clone is going to return null. So I'm just making sure as well that when I try to deallocate cleanly a null pointer, it works, which I already tested before, okay? But I just want to make sure. So clone of, it's not S5 anymore, it's S0, is going to be S8. And then clone of S1, which is an empty string, just the end of string marker, is S9. So let's modify all of this, deallocate, but let's make sure that everything goes smoothly. So I'm going to comment out the old stuff, all of this. There we go. This up to here. I don't need to see that anymore. I'm testing cloning only right now. So save, compiling. So the clone of hello is hello, yes, we already knew that. The clone of null is null, okay, that makes sense. The clone of an empty string is an empty string, okay, we are handling all the base scenarios here. Next step, Hsl Gather. So Gather is meant to take two strings. So let's go to the body of the function here. It's meant to take two strings as argument, allocate a new string that is big enough to contain both of those strings, so all the character from S1 plus all the character from S2 plus one extra character for the \0 at the end, okay? And when I say all the characters of S1, I mean all the normal characters. I'm not counting the backslash 0, okay? So I want to allocate a bigger string pretty much, and I want to make sure that I store inside of it, the concatenation of S1 immediately followed by S2. So again, this one should be relatively straightforward. Let's go here. So let's start by measuring the size, because we need to know how much we need to allocate. So int size1 equal Hsl length of S1. Int size2 equal Hsl length of S2. So far so good, okay? And then I'm going to compute the total size that I need to allocate. Actually, you know what? No, it's not even worth it, because I have already a function that is smart enough. Char star p equal str hsl allocate, and I'm going to give it size1 plus size2. So size1 is all the characters without counting the end of string marker. Size2 is all the character without counting the end of string marker for string 2. So I want a string that's big enough to hold all those characters, plus 1 for the end of string marker. But hsl allocate does that for me already. Whatever number I ask, if I ask to store n character, it's going to allocate n plus 1. So we are okay with that, okay? We are already taking care of this. Now, it's possible that hsl allocate returns null if something went wrong. Okay, if it's the case, I cannot do anything. So if not p, return null. I could not allocate the memory that I need. Forget it. I'm just returning null as a concatenation of the two strings. Otherwise, what I have left to do now, I have to iterate over every character of S1, copy them in the string pointed to by p. Then I iterate over every character in S2, copy them in the string pointed to by p, and at the end, I make sure there is a backslash 0. How am I going to write this? With while loop. Okay, so iterate over S1, while S1, star p plus plus, this is going to look familiar, this is kind of what we did before, okay, equals star S1 plus plus. So this is a one-liner that's going to iterate over S1 and copy everything into p. And then I'm not changing the parameter p. Okay, I'm keeping it as it is. And I'm just continuing the iteration. So I went through every element of S1, and I was copying them in P. Now I take S2, I go through every element of S2, and I continue copying them after the end of the characters from S1 in the string pointed by P. So here this is going to become S2 plus plus. This is going to become while star S2. And when I'm done, star P should point to the last allocated space in my newly allocated string, which is supposed to hold the backslash 0. So let's go ahead and put the backslash 0 right here. Okay? And then return null. Well, no, I would prefer to return actually, well, if I return p, here's what's going to happen again. We had that bug before, right? If I return p, now p is pointing at the end of the string. So I'm not going to see anything. So what I need to return is something that I'm going to call result, and I'm going to say char star result equals p. So I'm saving, where the newly allocated string starts. Then I'm incrementing that pointer p, so I'm forgetting where it starts, and I go up to the end of it, and then I just return result. So let's save this. And again, we are going to compile, run. So if I run, of course, there's no test. I'm going to do just one test real quickly on this one. And I'm going to say printf concatenating %s plus %s is %s. There we go. So I'm going to use, so which one was our small? So concatenating S5, and let's scroll back up. I don't remember what the strings are saying. So let's concatenate S4 and S5. Okay, so concatenate S5 with S4 is going to give me Hsl Gather S5 S4. All right, let's see how this is working. Compile. 1. Concatenating hello and hello there is hello, hello there. Yep, that's pretty much what we were expecting. So that's it for the Hsl Gather. And the last one that we have to implement is Hsl Extract. So the role of Hsl Extract is you are going to give me some indexes in the string. So you're going to tell me, for example, I want to extract from the string every character starting at this index and all the following character up to that index included. Okay, and that's going to kind of return to us a substring, but the substring is returned as a newly allocated string, so it's completely independent, and it's going to hold a copy of all the characters between indexes start to end, both included. So let's take a look at how we're going to write this. So I'm exactly where I need to be, so awesome. We are going to start by computing, the length that we need to copy. So it's going to be end minus start plus 1. And then we need something that is big enough to hold all of those characters. So char star, I'm going to call it P, equal Hsl allocate that length. Okay, so I measure the difference between the indexes. Now I pass that to str allocate. It's going to allocate that many characters plus 1 for the end of string marker. So now let's try to get rid of things that go wrong. For example, if Hsl allocate was not able to do his job, then I return null. If it returns null to me, I return null as well. Okay. If the string that you gave me is null, return null. And that should be actually done first thing. Okay. We should not even bother measuring the size or stuff like that. If the string that you give me that you want to extract something from is null, I cannot extract anything from a null string. I return null. Okay. Similarly, if end is lesser than start, you messed up. Okay, you're giving me bad indexes. Start should be lower than actually end. Other possibility that can go wrong if end is greater than Hsl length s. You're telling me that you want me to stop at an index that is past the end of the string. That's not going to be good. Okay, and same thing if start is lesser than 0. Yeah, we don't deal with negative indexes. Okay, so return null. And I think that I don't need to test if end is lesser than 0 because I tested if start was greater strict than end, so that should be okay. So all of those are very easy cases where I cannot do my job, so I return a null. Okay. At the end, I check after allocating, if the allocation went okay. If it went okay, I'll continue. If it didn't go okay, then I'm going to return null. And at this point in the code, now I'm ready to do the job. I'm ready to do that extraction, that copy. So I'm going to use a for loop to do this. And I don't think I need more than one statement, so we'll see about that. I'm going to say that I need int I. Actually, you know what? Let's declare int I equal 0 here. So I'll be redundant, but I'm going to set it to 0 here. Sorry, set it to start, so it's not redundant after all. I'm going to set it to start. I'm going to go up to the index that you gave me with the parameter end, and I'm going to increment it every time by 1. So this is me going over every character that you mentioned you wanted to copy. And then the copy is going to be a matter of writing inside the string pointed to by P, the one that we allocated, what we have in our original string. So original string, the index is going to be I. And this one, we need to do a little bit of index arithmetics. It's going to be I minus start. Okay. All right. And if I do this, I copy all the characters, but I'm still left with, the Where is my backslash 0 at the end? Not a problem. P index I equals backslash 0. And we should be good. And of course, we want to return P. So I can return P here because I didn't increment P. I didn't use pointer arithmetic on P, right? I just use array indexing. So I didn't modify P, so P still points to the beginning of the string that was allocated, so I can just return P. I don't need to save its value, sooner in a variable result or something like that. So let's try something here. What do we have that we can use here? We're going to use hello. There we go. S4 hello there. So printf extracting. So hello there, Hsl. So 0, 1, 2, 3, 2 to 3. Extracting 2, 3 from. That's going to be hello there. Is. That's going to be the result. So I'm extracting 2, 3. So Hsl extract. The string is, what did I do? S4, I think, right? S4, 2, 3, and let's see if that works. Compile first. Format %s expects the matching string. Yes, I forgot completely to give the original string, so that would be S4, comma, Hsl extract. Let's see. Oh. Extracting 2, 3 from hello there is LL, so H is index 0, E is index 1. The first uppercase L is index 2, the second uppercase L is index 3. Yeah, that's exactly what we needed. So, all right, I hope that those specific exercise gave you a sort of wide view of how to apply, what we learned about strings. I hope they give you kind of an understanding of how behind the scene the standard library string functions are implemented, so that they are not like magic, black box functions that you use without really understanding. As always, if you have any question, post in Piazza forum, whatever we're using this semester, or even better, come to visit myself or one of the TAs during office hours, and we'll be more than happy to go over some of the aspects of this video if anything wasn't clear. As usual, thanks for your attention, and I'll see you in the next video.